Thank you. Hi, my name is Amit Majumdar. I'm from the San Diego Supercomputer Center, and I'll talk about a campus cluster that we have at our university, serve the UCSD researchers, graduate students, postdocs, as well as undergrads. And then as a part of that, we got a NSF grant, which allowed us to implement a DD and IME, so I'll talk about that. So again, this is the Triton shared computing cluster. This is a UCSD Condo cluster, which means UCSD faculties buy some number of nodes. New faculty joining UCSD, they have a startup package where they join UCSD. They can buy clusters, some nodes, and we manage the nodes for them. And the benefit of that is they can use the number of nodes that they buy, for a whole year round, but they can expand out to other nodes in the campus within some constraint, of course, for certain number of hours and things like that. So many universities have these kind of condo clusters for their faculty, and we have the same thing. It has GPU nodes, it has 30 participating labs, is growing. It's very popular. So it's interesting that UCSD can attract big name faculty saying that we have the condo cluster, and they for their genomics and life sciences research. A lot of people like that. So again, as I said, it enhances the research competitiveness of UCSD for UCSD researchers, as well as for the graduate students, and it's cost effective for UCSD researchers. So the way it works, as I said, group 1 buys condo, group 2 buys condo, but actually group 1 can use in not only on their condo nodes, but on the condo nodes of the other of the cluster within some constraint of say 8 hours or so, and I'll mention few of those later. So there are two ways of using it. One is the condo users, as I mentioned, and another is the hotel users, which is they pay for usage at certain price. So anyone from outside of the condo group can also pay for the nodes and just use them. So as a part of that, we wrote a proposal to the National Science Foundation, and it's called, the title of the proposal was BioVerse, which the focus was, we noticed the type of applications running, and it was a lot of bioscience, bioinformatics, genomics applications, and we noticed that the workload of those applications, and casted the proposal so that those workloads can be effectively used on the machine. So that was the focus of the proposal, how to improve performance of workload, which was primarily genomics, bioinformatics, life sciences. So it was an award from the National Science Foundation. Pretty much all of it was equipment award. And then again, the overall objective of the BioVerse also was to increase the research effectiveness and productivity. And one motivating example was small block, small file I/O performed by codes like GATK for processing of genomics data. So again, the science use cases were genetic cause and treatments for brain disease, role of gene expressions, and human vaccine research project, and some autism research, molecular basis of autism research by Jonathan Saga. So the key features of the proposal that was funded by NSF was this IO accelerator, that's the DD and IME, with flash memory and software, and a FPGA-based EDICO genomics Dragon network that also processes these genomic pipelines very efficiently because it's FPGA-based for optimizing those genomics pipelines. We had a 672 core, I think that's 24 nodes of processors, and we integrated with Lustre file system. And the job scheduler was also tweaked to allow life sciences applications. So the Dragon nodes, again, as I mentioned, is a FPGA-based genomic pipeline processing appliance. And that does various kinds of genomic pipelines in different formats like FASTA and BAM files, and optimizes their processing at a very fast pace, even if it's FPGA-based node. So as a part of that NSF grant, we got this Dragon node, as well as 24 regular Intel nodes. and the DDN, and it was all integrated with the cluster file system of about 700 terabytes that already existed as a part of the campus cluster. So here is the overall architecture. The things on your right is what was the NSF funded project provided. Basically the BioBurst is where you see the IO accelerator, the Dragon nodes, and the regular Intel nodes. And the DDN IME is what the 500K from NSF allowed us to purchase, and all focused on improving life sciences, biosciences, bioinformatics applications and their IO behavior, because that's what we noticed was the primary workload of this campus cluster. So it was a very nifty proposal, really honing down on the workload, the science use cases, and saying these are the hardware, software resources we need to improve those workload, and reviewers and NSF like that. So obviously, I don't need to talk about this much. Why IO is important is all kinds of IO, from producing terabytes, petabytes of data to someone writing thousands or millions of small files for genomic applications. These are all hard problems. IO is very hard problem. IO can be a primary bottleneck or primary variation of applications performance, more so than compared to single processor performance or MPI scaling, which are relatively stable. Whatever performance you achieve on them, single processor or MPI scaling may not be big, but stable. But IO can be very variable because a lot of people share in the same shared IO infrastructure. As the whole systems get complicated, IO become more and more of an issue. We have different kind of hierarchical and configurable storage solutions. You have node local SSDs, you have burst buffers, you have complex checkpointing applications are doing, redundant fault current checkpointing. So things can get very complicated. And obviously you have a lot of tools and software, the scalable checkpoint restart software being developed with a huge DOE grant for exascale programming from Lawrence Livermore Labs. A lot of complications in IO, and it's important to understand and stabilize IO performance. So how can we enhance users' experience was the focus. It's not so much performance, but you enhance their user experience so they can do bigger, better science. That's what makes a university competitive. So now quickly go back to as I mentioned, the theme of the talk as it relates to this DDN and performance a little bit. Again, I don't want to focus on performance, but more on usability and getting more broad science done. So basically, as I said, we had a luster already set up, but we got the DDN IME appliance as a part of this 500 KNSF GAN. So we use some benchmark, standard IOR benchmark and the GATK application to look at how applications will behave and perform on the architecture. So here is the the IME architecture. As you can see, the home file systems are there, and about 750 terabytes of luster file system already existed. It goes to the 100 gigabit Ethernet switch, but compute nodes and the Dragon node is what we purchased as a part of the 500 KNSF grant, and then in the DDN appliance, as you can see, with the EDR IP switch, the IO accelerator, and it goes to the same parallel cluster file system. So I will provide some numbers between LFS and the cluster file system and IME, but it's not an apple and apple comparison. As you see, one goes to the gigabit and another is going to EDR. Again, but our focus is science, productivity of science, not necessarily performance, and finding solutions for the bioscience and bioinformatics applications, which has a lot of small files and small IO. That's why we got the DDN IME appliance for this our campus cluster. So again, we use the TSCC, which is the Triton shared compute cluster, name of the machine at SDSC. We took two of the Intel nodes that we purchased as a part of the NSF GAN, and we benchmark on cluster file system on IME. We use the IOR, and many of you know the IOR benchmark. It lets you control various kinds of IO. and the GATK, which is a genome sequence processing software heavily used by the bioinformatics and genomics community. So IOR is developed Livermore to benchmark all kinds of IO. It gives you all kinds of control over the size, transfer size, and access mode. I'll not go into this detail. These are the input parameters of the IOR that provides you with all kind of control over the types of IO, bandwidth, number of files written IO that you want to measure. So we use the IOR on these two BioVerse nodes, and so here at whatever is looking at the orange color is the IME performance, and the blue is the luster performance. It's very hard to read, but at the bottom it has both read and write. It has both. I think some of them are read and write. I think it disappears on the thing. Okay. Read and write performance for different file sizes. The file size goes from like 4K to about 32K on the plots here, and the write plots are for IO ops, and then so IME performance better. But again, we are not focused on performance, but more on providing solution to the small file issue that genomics and bioinformatics applications we are seeing at UCSD from UCSD users. Is the same plots, but for a larger file size. I think it goes on the here from 64K to about 2 million bytes, the size of the file. You can still see that IME performs better for this kind of test we did, but the luster also seems to improve as expected for larger file size. And so then we ran this GATK genome processing software on the 4 nodes of the TSCC machine, and you can see that the orange color is what the IME performance is, and it completes within about, I think, 65 or so hours. But the luster one was still did not complete, and I think needed more hours to complete. That's one thing. Another thing is these are the lots of runs, and you can see on the IME the variation is very small of all the runs, where for the luster the variations are a lot more. But there are a lot of real life issues going on. Luster is being shared, other jobs are running on the luster file system and things like that. So I don't want to focus too much on performance itself. It's like for us, it's the finding the solution. The small file IO bioinformatics application was a problem for the users. So we were looking for a solution, not improving performance. Solution allows you to do better science, a lot more science. Performance is represent results of performance from computer science point of view. That doesn't help a scientist. A bioinformatician is not interested in performance. He or she is interested, able to do a lot more science with his grad students. So anyway, that's that.